that brings us to our headline speaker. So Professor William van Winjaarden, Bachelor of Science in Computer Science and honors Bachelor of Science from University of Windsor in 1982, followed by a Master's and PhD in Physics from Princeton in 1986, and has been a professor at York University for the past 36 years. He's a contributor to CO2coalition.org, a signatory to clintel.org, and he was advisor to the Ontario government as well. So I'll let him speak a little bit more about himself as well, but please join us in welcoming.
Well, thank you very much. Can you all hear me in the back?
Absolutely, yeah.
Well, it was a pleasure to drive up from Toronto for my wife and my son and I this afternoon. It's nice to have a respite from seeing the natural environment consisting of concrete and asphalt. So I envy you in this beautiful environment. So I'm going to be speaking today about climate change, or perhaps the lack thereof, and basically showing you the evidence. And so the first question we'd like to address is the climate of the Earth constant? I think we all know the answer to that is no, because 10,000 years ago, where we're sitting now, we had a layer of ice covering the surface of the Earth about 1 kilometer thick. It looked a lot more like Antarctica. But that was a long time ago, so we can say, who cares about that? We want to know what happens in recorded human history. Was the climate constant during that period of time? And the answer is no. And here is some nice evidence on the left here. Here we see the remains of a Catholic church in Greenland. This was a location where the Vikings went and settled. They farmed. They have found the remnants of a few thousand farms where people farmed with sheep and goats. The climate was warmer in the northern hemisphere, and farming was possible in Greenland. Then around 1400, the settlements were abandoned. I think the last date we have is something like 1408. There was a couple that got married. They went for their honeymoon to Iceland, and the date of 1408 was stamped in their passport by the Iceland Department of Homeland Security. So for some reason or other, the Viking settlements were abandoned, we think because the climate got colder and farming became unrealistic. In fact, in Northern Europe, we had the Little Ice Age, a period from about 1400 to 1800. Rivers such as the Rhine, the Thames regularly froze. And so here's a nice iconic painting done by Hendrik Averkamp in 1608. If you look closely, I don't think you could see it too closely. I'm always a little leery of showing this in Canada because you see some people playing hockey. But I usually get audiences are reassured when I tell them these gentlemen were the great-great-great-great-grandfathers of Bobby Orr.
Yeah.
So climate is not constant. Now, of course, what we're here today to discuss is what's happening to the climate as a result of the use of fossil fuels that generate greenhouse gases, most importantly carbon dioxide, methane, and nitrous oxide, or N2O. And there have been some very nice measurements made of these concentrations in the atmosphere. CO2 has been going up. Here we see measurements from 1960 to about 2020. It's gone up from about 320 parts per million to about 420 parts per million. It goes up by about 2.5 parts per million, basically because we're using oil, natural gas, coal. You also see the line wiggles a little bit. The reason for that is when we get summer and spring in the northern hemisphere, the plants start to grow and they suck out the CO2. CO2 really is plant food. Now there's more land in the northern hemisphere than in the southern hemisphere, so there's going to be a net change in the amount of CO2 from winter to summer. So that's responsible for the little oscillation on that curve that is steadily increasing. Methane has gone up also, but notice it's kind of plateaued in the late 1990s, early 2000s, and we don't know why. The only reason that I've heard is, well, us Westerners went to Russia, and Russia had some leaky pipelines. The communists couldn't do anything right. And then we told them how to make pipelines leak-proof, and then they didn't leak, and that's why methane stopped going up. Well, I'm not entirely certain I buy that argument. I would love to see some measurements of the methane concentrations near where those leaky pipelines in Russia were, and I've never seen them. So it was going up, it plateaued in the late 1990s, and it's gone up in the last decade or so. Nitrous oxide, this comes largely from fertilizer use. This has gone up from about 320 parts per billion. These here are parts per million. So 320 parts per million to 330 parts per million. Sorry, 300 to 330 parts per billion in the last 40 years. And this comes from fertilizer use. Now, of course, the fuss is that people say these are greenhouse gases. That means they can transmit visible light, but heat they absorb. So they prevent heat going from the surface of the Earth back to outer space. And this is, the theory goes, causing some warming. And so here we see the temperature change from 1850 to 2025. So this goes from about -3/4 degree to 1¼ degree. Now what is interesting about this graph is you see from about 1900 to 1940, the temperature went up by about 1/2 degree. Now, no one really knows why that occurred, because during that time, greenhouse gases were not changing very much. So probably this is not due to greenhouse gases. This is probably just some warming that continues after the end of the Little Ice Age. Then from 1940 to about 1980, temperatures remained flat, maybe they decreased slightly. We don't understand that too well. The thinking is, well, maybe there was a lot of pollution, and the pollution acted to prevent global warming from occurring. And so then the theory goes, well, in the 1970s, we in the West, we became very concerned about pollution. We had a lot of pollution controls. The air got cleaner, and sure enough, then the temperature after 1980 went up because we had cleaner air. The problem with that is if you go to India or China, after 1980, the air did not get cleaner, it got much, much dirtier. So this idea that we in the West control everything, I think requires some caution. Then from about 2000 to 2016, surprise, surprise, temperatures remained flat. This was completely unexpected. None of the models, which I'll be talking about soon, predicted this. And this is known as the global warming hiatus. And so you had conferences devoted to why did this occur. In the last few years, we've seen an increase. Last year was a warm year. It was one of these El Nino years. You have this big blob of warm water in the southern Pacific, and this causes warmer temperatures around the Earth. So the point I'm trying to make here is that CO2 has been rising steadily, as have N2O, and yes, methane has been going up. Temperature, on the other hand, goes up, flat, not quite the same pattern. So there's more to temperature than just saying what's the CO2 concentration. Now I refer to these models, and there is a United Nations group called the Intergovernmental Panel on Climate Change, and they've been trying to make sense of what's going to happen with the world temperature. And so they have very elaborate computed models, and they've made predictions of temperature warming from 1975 all the way out to 2020. And that's basically this spaghetti here. So there are like 50 different computer models. And that spaghetti is difficult to interpret. So if we take the average of all those models, we get these nice little red or yellow dots. And here's a line put through the average of something like 50 of these computer models. Now the question is, what were the observations? And the observations here are in green. And so it doesn't take a rocket scientist to immediately see that the green line slopes up much less than these models. So the models greatly inflate how much warming there has been. This is well known that there is this hot warming problem with the models. Much of the reason probably is because clouds are very difficult to model on the computer. Now, what have we done? I've worked with Will Happer at Princeton, and we generated this graph. So what we've done here is we plot heat. This is heat measured, say, by a satellite versus color or frequency. Now, these colors are in the infrared, so this is not colors that you can see. Your cat probably can see a little bit in the infrared. So you can think of these as infrared colors. Now, if there were no greenhouse gases, then what your cat in the satellite would see is this nice blue curve, this nice bell-shaped or funny bell-shaped with a tailed curve. Now, if I add the greenhouse gases, water vapor, CO2, ozone, methane, and nitrous oxide, I get this black curve. Now, the reason for the difference between this nice blue curve and this ragged black curve here is because there's a lot of absorption of the infrared heat by water vapor. This big dip is due to CO2. Here, this second dip, that's ozone. This here, the difference between the blue and the black curve, that's mainly due to water vapor. A little bit due to methane and nitrous oxide. If we double the CO2 concentration from 400 to 800 parts per million, we get this red curve. And you notice the red curve and the black curve nearly overlap. The difference between the red curve and black curve is what the fuss of global warming is all about. If we have 0 parts per million CO2, we get the green curve. So this clearly shows this is what carbon dioxide is doing. It's absorbing infrared light of these frequencies, about 600 wave numbers. Now, you're probably thinking, William, that's a nice curve, but why should I believe you? And that's a fair question to ask any scientist. And the answer is, well, we're going to look at observations, and we're going to show that we can account for those. So here we have our satellite with our cat looking down. Here are the observations. So this is intensity of the heat coming to the satellite versus frequency or color. And so here we see for the Sahara observations, this is what we calculate. Looks pretty similar. For the Mediterranean observations, here's what we calculate. You can't see the scale, but these numbers here are not as high as for the Sahara. The Sahara is warmer, so you're going to get more heat going to the satellite than when you're over the Mediterranean. And Antarctica, here are the observations, and here is our model. We do not have any fudge factors in our calculation. So we're kind of pleased with this agreement between the model and observation, and that indicates that we have some understanding of the situation. Now let's try to understand how much of the warming is due to each of these greenhouse gases. We're going to assume that the warming in the 21st century due to greenhouse gases will be about 1 degree C. Where did this 1 degree C come from? Well, the observed warming in the 20th century was about 1 degree C. Probably a lot of that from 1900 to 1940 had nothing to do with greenhouse gases, but that's why 1 degree C is a nice number to pick. Now, if we take, we're going to be considering carbon dioxide, methane, nitrous oxide, and then halogenated gases. Those are those CFC compounds that you used to use in your spray cans. There are a whole bunch of these gases and their replacements. They also act as greenhouse gases. Now, if I add 1 molecule of methane to the atmosphere, it exerts about 31 times greater warming than adding 1 molecule of CO2. So that's why people always complain methane is so dangerous, because 1 molecule of methane is 31 times more terrible than 1 molecule of CO2. But we are adding about 300 times more CO2 molecules to the atmosphere than methane molecules. So the net effect of methane will be the 31 divided by 300 or 312 if you look at it carefully. So the effect of methane is about 1/10 the warming of CO2. Now if you look at nitrous oxide, add 1 molecule of nitrous oxide and it exerts about 233 times the warming as 1 molecule of CO2. But we're adding about 3,000 times as many CO2 molecules for each single molecule of nitrous oxide. So the effect of nitrous oxide is 233 divided by 3125. It's about 6% of the warming compared to CO2. If you do the same calculation for these CFC type compounds, you get a contribution of about 0.02 degrees C per century. So CO2 warming per century about 0.83 degrees C per century, methane 0.08, N2O 0.06, and these CFC compounds 0.02 degrees C per century. If you look at your thermometer, I think you'd be hard pressed to measure 100th of a degree.
What about water vapor?
Well, water vapor we can't really control. Now, I think your question was, I'll get back to it later, is if you have some warming, does that cause an increase in humidity? And that's one of these feedbacks, and I'll be happy to talk a lot more about it later. Now, is CO2 very bad? Well, I began by saying CO2 is plant food. And here we have a little experiment. You can't see it too well, but this professor grew this pine tree in a plastic bag, and he fed into this just the normal atmospheric pressure of CO2. Here he added 100 plus 150 parts per million CO2. So instead of, say, 400 parts per million CO2, he was at 550. And you see the plant starts to get bigger. When he adds 300 parts per million CO2, still bigger, 450, so that's more than double the CO2 concentration. The plant is noticeably bigger than the ambient tree growing in ambient atmospheric conditions. So more CO2 means greater plant growth, which is great for farmers. But there's some more subtle effects. It turns out when you increase the amount of CO2, the holes in the leaves called the stomata, they shrink in size. So it's a bit like having a bunch of teenagers. If you put a lot of food in front of them, their mouths become smaller. Now, if the stomata shrink in size, that means there's less water loss from the plant. And that means the plant can grow better in drier areas. And so there have been some studies by NASA, and they come up with this. And green here means that vegetation is growing more than what you'd otherwise expect. So you see in the border of the Sahara where it's very dry, plants are starting to grow more rapidly. So the point is having more CO2 introduces some subtle effects that assist plant growth. Now, one of the greenhouse gases is nitrous oxide that comes from fertilizer use. And we can ask, why has fertilizer been used? Well, if you look at the yield, so this is the ratio of the yield compared to the yield in about 1860 or so. So here we go from 1850 to 2030. You see the yields of everything, be it corn, wheat, barley, hay, oats, rye, etc., have gone up very sharply. And the increase occurred very rapidly after World War II when people started to use better seeds and also fertilizer. So if we say we are not allowed to use fertilizer, and yes, some countries, prime ministers want to say that because they don't want to have nitrous oxide increasing in the atmosphere, that means you're going to have a drastic decline in the world food supply, probably even famine. And what increase in temperature are we looking at? Less than 0.1 C per century. I would argue having a stable food supply certainly is better than worrying about that. Now, if you have a warming temperature, there are all kinds of effects that you can expect or are predicted. One is that you get less ice. So I think you're all familiar with the Arctic ice disappearing. You have the lonely polar bear struggling to remain afloat on a little ice floe. We've been measuring the extent of the Arctic ice from 1979 onwards. It goes up and down. The minimum occurs in September. The maximum occurs in March. So here you see this going up and down. And then I put a blue line on the average March extent trend, and this red line is the average extent in September. And if you were to continue this red line, you would hit zero ice extent in September of something like 2075. But if you look a bit more carefully and you look at from about 2007 on, and then you just fit those September ice extents, you just get a flat line. So we don't quite understand what's going on here. The Arctic ice did go down noticeably in the 1990s, early 2000s. But in the last 16 years or so, it seems to have stabilized. Nevertheless, there has been a decline in Arctic ice, and this has some dramatic observations. I thought this quotation was interesting. The expedition sailed as far north as 81 degrees, 29 minutes in ice-free water, so this is very far north. The Arctic is not recognizable as the region of the previous 50 years. Glaciers have been replaced by mounds of earth and stones. Great shoals of fish have disappeared, and the seal population has diminished. And this was by G. Ift, entitled The Changing Arctic, in the Monthly Weather Review, page 589. Whoops, I forgot the year, 1922.
Oh, wow.
So the Arctic has changed in the past. There have been warm periods, some followed by cold periods, and we don't quite follow that. However, our ice extent has changed. For example, if you go to Banff National Park, I'm sure you can see the dates of the retreating ice. One of the best places to see the retreating ice is in Glacier Bay. I have a sister-in-law, one of these rich accountants who retired and could afford to go on a trip to Glacier Bay, Alaska. And apparently it's really nice to see. You see some beautiful pictures of glaciers. The first cruise was done by Mr. Vancouver in the late 1790s, although he couldn't get far because the ice extended all the way to the Pacific Ocean. And they have mapped out the decline of this Arctic ice. Each of these red lines are a different date. And you see that the Arctic ice has retreated by about 100 kilometers. Much of that retreat has occurred during the 1800s, when greenhouse gases were not changing significantly. So there has been a retreat of glaciers. Much of this is due not to increased greenhouse gases. Now, of course, if you have a decrease in ice, that goes to increase in sea levels. And some of you probably recognize that my name is Dutch, and one of the questions I get often is, William, why are you so tall? And I explained that my ancestors came from Holland and the short ones drowned. If you look at the map of Holland, about 500 BC, it looked very different than what it looks like today. In fact, today, all those purple regions are below sea level. If you did not have dikes, you would have fish swimming there. It's about 4 to 5 meters below sea level. So this area here was very marshy. The Romans have given us accounts. They would be in their heavy armor chasing a barbarian, and then they would sink into the swampland. So we have had an increase in sea level about 5 meters over 2,500 years, and that works out to something like 2 millimeters per year increase in sea level. Now, a more recent measurement is here, sea level from about 1860, sorry you can't see that too well, to the present day. And this blue curve is the measurements. These measurements were taken up here, placed in Friesland. And then they fit a nice line through it. And this line slopes up at 1.5 millimeters per year. So this is entirely consistent with the increase in sea level we would get from those two maps. Also shown in this bottom graph is the CO2 concentration in green. My apologies for the poor view graph. So this CO2 has gone up from about 280 parts per million before the Industrial Revolution to about 420 parts per million right now. Now the point of having those two curves on the same graph is that here you see the CO2 going up dramatically, but the sea level just seems to be going up at a steady pace. So again, CO2 does not seem to be causing an acceleration in sea level. Now the reason I trust the Dutch very highly is if you're a Dutch person and you get this wrong, your family drowns. In fact, in the 1950s, there was a big storm, and some of the dikes surrounding where my parents grew up burst. And when Canada heard about it, they expedited their application to immigrate to Canada. So I guess I'm descended from some of the world's first climate refugees. Now, if you're a farmer, it's not just temperature that worries you, it's also adequate rainfall. And so the worry is, if we have a warmer atmosphere, does rainfall change? Well, I looked at the data. This is from the United Kingdom. Here we look at the percentage change of precipitation from 1700 to the present day. This red curve is just the average of 5 of these angled black dots. And basically, in England, precipitation doesn't change. It's just very reliably wet all the time. If you look at India, Pakistan, you see a lot more fluctuation. In fact, when I was doing this, I noticed 1900, only half of the annual precipitation. I thought, how can that be? And so finally, I Googled 1900 India famine, and it came up right away. The monsoons failed. And as a result of this, several 100,000 people, maybe even 1 million people, starved to death. It was terrible. So I was walking across campus a week or so later, and I saw my friend from engineering, Jit Sharma from India, and I said, Jit, you know, I looked at the precipitation records in India, and I saw in 1900 there was a terrible famine. And he looked at me, of course, William, every school child in India learns that, didn't you? And I had to kind of cower and say no. And 1900, all we were told at my British school was that Queen Victoria was dying. So this certainly agrees with historical history. In the U.S., if we exclude Alaska and Hawaii, no dramatic change. If you look at California, you do see a lot more fluctuation because California, much of it is a desert. Some years are very dry, some years are very wet. However, from 1850 to the present time, you don't see any trend. Now, one of the things that you probably have heard about is wildfires. I think last year was a terrible year. So here we plotted, red is the area burned, black is the number of fires, and up here we have Canada. And you see from 1990 to 2020, some years you have more forest fires, more is burned, some years you have less. I wanted to update this to get the statistics for last year. I couldn't get that. But I'm sure last year would be way up here. But please keep in mind there are other years that were way up and others are way down. Closer to home in Ontario, the same thing. Some years you have more forest fires, some years less. No overall trend.
Excuse me.
Yeah.
What consideration is given to deliberate?
Well, there's a lot that goes in here that you would expect there to be a trend due to humans. So, for example, one of the things we've been doing is trying to suppress fires. And if you suppress fires very successfully, you get a buildup of flammable material, and then you're going to have a year where you get extraordinary amounts of fires. You have other effects, like you can have campers going in there and setting blazes. So the point of this is not to show that there's no human effect. But what the climate change people, or some of them, like to claim is that there's been a dramatic increase in forest fires due to climate change. And what I'm trying to point out here, there is no recognizable increase in either the area burned Now, one of the things that people have said is if we have more greenhouse gases, we're going to get more storms, more extreme events. Well, what are the big extreme events that you consider? Obviously, hurricanes. So here we plot the number of all hurricanes from 1980 to the present day, up here. Some years you have more, some years less, no overall trend. And here you have major hurricanes, which have much higher wind speeds. You have fewer of them, again, some years more, some years less, no overall trend. So nothing's happening there. Another extreme event is tornado. Now here we plotted a number of tornadoes from 1995 to 2020. The reason we've taken that segment of time is the measurement instrument remained the same. It's what they call the Doppler instrument, which measures your wind speed. This didn't exist in the 1980s. So when you're looking at the number of events, you like to make certain that the instrument remains the same, because if you change instruments, you can get a change in how efficient the instrument is at detecting something. So if you look at the number of tornadoes from 1995 to 2020, some years a few more, some years a few less, nothing going on. If you look at the strongest tornadoes, the same story. No overall trend. Now, one of the things that people have said is if we produce more CO2, a lot of the CO2, up to half, goes into the atmosphere and goes into the oceans. And when it goes into the oceans, it creates something like carbonic acid. So the story goes, what we're doing is we're slowly turning the oceans into pulp, acidifying them. And we all know if you put a fish into stomach acid, they get seriously unhappy. So the pH scale is what's used to measure acidity. When it's neutral, like distilled water, we're at 7, bleach is about 13, stomach acid about 2. And so we've done the calculation. If you double the amount of CO2 in the atmosphere, the pH will be reduced by about 0.27 of those pH units. Now, how does that compare to the real world? Well, here are some measurements taken at Santa Monica. This is a place in California from about 2000 to 2006. So you can see it takes about 6 years to get your PhD at Santa Monica. And what they've done is they've taken a PhD student, tied a thermometer, a pH meter to him, and then he goes up and down like a yo-yo for 6 years. And you can see here, orange, that means there isn't that much CO2, because near the surface there's a lot of sunlight, you get a lot of plants growing, and the plants suck the CO2 out of the water. It's only when you get deep down, where there are very few plants that suck the CO2 out, that you get more CO2, and you get a slight increase in acidity. So you can imagine if you have a sunbathing seal, and after an hour or so she gets hungry, she dives down 50 meters, she's going to experience an increase in acidity of a few tenths of a pH, comparable to what you'd expect if we double the CO2 concentration. Seal isn't doing any badly due to that change in pH, nor will we. So our conclusions. If we extrapolate the observed 20th century warming of 1 degree C to the 21st century, and now I'd like to get back to the very good question someone asked about water vapor. That 1 degree C, that presumably includes an increase of water vapor triggered by those increased in greenhouse gases. So when we say 1 degree C increase, that includes the effect of water vapor increasing possibly due to those increasing greenhouse gases. We've also calculated in detail, but that gets a bit beyond the scope of this talk. I can talk to you afterwards if you wish. The amount of warming for CO2 we expect will be about 0.83 degrees C per century, methane 0.08 degrees C, nitrous oxide 0.06 degrees C, total warming about 1 degree. If someone says, William, I don't like your 1 degree, this should be 1.5, then multiply all those numbers by 1.5. For example, 0.08 times 1.5 gives you 0.12, still very small. 0.06, 0.09 degrees C per century. Canada's fraction of emissions, 1.5% of the CO2 in the world comes from us, about 1.1% of methane, 1.4% of N2O. So if we multiply these two numbers together, then we see Canada causes about 0.012 C per century warming due to CO2, 0.0009 degrees C per century warming due to methane, 0.0008 degrees C per century warming due to nitrous oxide.
The calculation of methane, is that including the methane that's being released in the Arctic where soils are being exposed as a result of the retreat of the ice?
We're using the global emissions due to methane, so that includes that effect, it includes leaky pipelines, it also includes methane which comes from burping cows. Cows eat grass and then they chew their cud and then they release methane, so it includes all of those effects. We have also in our calculations said let's presume that methane continues increasing at the rate from 2003 to the present time, where methane was going up. If you consider that earlier period, methane was flat. So we have taken the scenario that makes this number for methane as large as possible. The evidence doesn't support any hysteria about droughts, floods, polar ice, glacial retreats, sea level rise, etc. There is some warming, however, it is modest. And I would argue if you're a Canadian and it is -30 or -40 degrees C outside, and you don't want to burn your furnace because you're afraid of global warming, that's fine, but you probably are going to freeze to death.
Right.
And if you're worried about this nitrous oxide increasing, which is at this very, very tiny rate, you can of course not use fertilizer on your garden. You cannot use fertilizer anywhere in Canada or the world, and then a lot of people are going to starve to death as well. That's probably going to be silly as well. So outlawing fertilizers, reducing birds, which is now being talked about actively in countries like Ireland, Holland, and I believe also in Canada, negligibly affects the climate and endangers the global food supply. There also are unintended consequences. If you take, say, a hectare of very fertile land in Canada or Holland out of production, people are going to eat. That means they're going to turn some of the Amazon rainforest into farms. That land in the Amazon is not very fertile. So if you have, we'll say, 1 acre in Holland, you might need to have 10 acres in Amazonia. And of course, those 10 acres in Amazonia, after a few years, you have to replace with another different 10 acres of Amazonia. So those policies may inadvertently do great damage to the ecology. So the world is not close to a climate crisis in 10 or even 100 years. So net zero just is not based on science.